Hello everyone, my name is Mujo Durmisevic. For my final project, I've decided to plot shear force, bending moment, deformation slope, and displacement along the loaded beam, using differentiation methods and simulating. For some background information, there are different ways to support a beam. To the left, we have a roller support. A roller only offers a reaction in the Y, but allows for movement in all other directions. Fixed support does not allow for movement in any direction, along with provides a moment resistance in all directions. A pin support is similar to a fixed support, except that it does not provide a moment resistance in the Z direction, so this beam can freely rotate around the Z-axis. When a beam is loaded, internal loads form. In 2D, these loads are looked at as the vertical shear force, the axial normal force, and the bending moment. In 3D, we have these same three components along with the addition of others, and each component will form only if needed depending on how the beam is loaded. So for shear moment diagrams, we consider only the shear force V for the shear diagram and bending moment M for the moment diagram. So here we have an example of a beam supported by a pin and a roller and loaded with a uniformly distributed load of 3 kilonewtons per meter. The first step would be to find the reaction forces at the supports. Since only vertical forces exist, to do this, we'd sum forces into Y and find the magnitude of each reaction to be 6 kilonewtons. So our shear diagram will start at 6, decrease linearly to -6, where the reaction at B will bring it back up to 0. With the information known and a shear diagram, the moment diagram can be formed. So here's an example of how to come up with shear and moment diagrams by cutting the beam at each foot along the length and summing forces into Y for shear values and summing moments for moment values. We then take these values and plot them along with the distances to get our plots. This can be quite time consuming, so another method exists which is much more efficient. This method is the method of integration. So, to get the shear equation, we take the negative integral w dx, w being the loading. We'd need to convert this loading into a y equals mx plus b equation. In this case, we got a constant slope, rho 0, so our equation would be y equals 3. And we'd integrate that along with a negative, because the load is pointing downwards, in order to get the shear equation. For the moment equation, we take the integral of this shear equation. So beam deflection is the deformation the beam will undergo once loaded. And the deflection diagram is also known as the elastic curve. The deformation slope, which is one of the plots we will form, is the tangent to this elastic curve at each point. So here's just an illustration showing the relationship between the moment diagram and the elastic curve. In a region where a positive moment exists, it will be apparent that the beam will be curving upwards. In a region where a negative moment exists, the beam will be curving downwards. So now that we know how to come up with the shear and moment equations, we can move on to finding deformation, slope, and deflection equations. Deformation slope solve for by just taking the integral of the moment equation, but dividing it by E and I. E and I is the flexural rigidity. E is the modulus of elasticity of the material, and I is the moment of inertia of the beam shape. After we find this equation for deformation slope, we can integrate it once more to get the deflection equation. Now that we have all the background knowledge we need, we can start an example. So the beam, 14 feet, shown is subject to a uniform distributed load of 1.8 kips per foot. Plot the following: shear diagram, bending moment diagram, deformation slope diagram, deformation curve. We're given E and I, but we have a little problem because our length is given in feet and our load is given in kip feet, but our E and I are in pounds and inches. So to solve this problem, we will convert the length to inches and the load to pounds per inch. So once we've done that, we can solve for the reactions at the supports. Since only vertical forces exist, the X reaction in the pin will be 0, but the Y reaction will be 12,600 pounds. So now we can move to Simulink. The first thing done is inputted 168 into the stop sign. This represents the length of the beam. So 14 feet times 12 will give me 168 inches. So to start off with, we have the equation of the load, the y equals mx plus b equation of the load. We integrate that to get shear. And like we've mentioned, the reactions at the supports with 12,600 on each end. And since this is a first order equation, it will decrease linearly. This x-axis is representing the beam length in inches. If we now integrate the shear equation, we can get the moment diagram. The moment diagram, second order equation, results in a concave down parabola, the max being at the midpoint of the beam. Now, if we integrate the moment equation, along with dividing it by E and I, which were given, shown here, we can get the deformation slope diagram. But first, we must solve for C. In the moment equation, we didn't have to worry about C because it was 0. In the shear equation, the C was the 12,600 reaction, which is the first thing that occurs in length. So to solve for C, we have 1 over EI, integral of our moment equation, and at what location is the slope known to be 0? Well, it would be at the midpoint of the beam, which is at 7 feet. Converting it to inches, we'd multiply by 12. So inputting that for x, we get a C of negative 29,635,200. And now we have our slope deformation slope diagram, which looks like this. And magnitude at each end would be about negative 0.0028 on the left, 0.0028 on the right. So now if we integrate this deformation slope equation, we can get our deflection diagram, which looks like this. And it will be max at the midpoint of the beam. So now we have plotted shear, moment, deformation slope, and deflection. We can check the values by using these predetermined equations. There's one for max moment, there's one for slope, one for max deflection. And if you observe the plots in these values, you'd see that they match. Thank you.